So I hope I am audible. A very good evening, all the participants, uh, and welcome from the Department of Physics, Bhairav Ganguly College, Belghoria. And this is the seventh initiative of organizing the national level webinar on cosmology. And today's resource person is none other than my close friend, Dr. Dhiraj Kumar Hazra. And Dhiraj is now the faculty of, let me introduce our today's resource person first. Okay. Okay. So today's resource person Dhiraj is the faculty member at the Institute of Mathematical Science, Chennai. Before that, was the he started his career and done his graduation from Jadavpur University, and then uh, integrated MSc PhD physics from Harishchandra Research Institute, Allahabad. Then he moved to Korea for postdoctoral research at Asia Pacific Center for Theoretical Physics, followed by PCCP Fellow at the Paris Center for Cosmological Physics, Astroparticle at Cosmology Paris. Then he was an INFN Fellow at the Instituto Nazionale di Fisica Nucleare Bologna, Italy, and then from 2019 to 20, he was the Mary Sklokodakuri Astrophyte Fellow. Oh, I am stumbling the uh, pronouncing the words. Pardon me. At the INAF Observatory di Astrofisica e Scienza dello Spenza di Bologna, Italy, under the mentorship of Professor Fabio Finelli, and he was also the associate of INAF there at Bologna, and now he is the faculty member at the Institute of Mathematical Science, Chennai. He's many of the among many of his research interests, some broadly uh, includes the inflationary cosmology, analysis of cosmological data, mainly data from cosmic microwave background, and reionization, possible deviations from standard model of cosmology, large scale structure, dark energy, degeneracy cosmologies, etc. So, with this brief introduction, I would like to introduce Dr. Dhiraj Hazra and invite him on behalf of the College of Belghoria to deliver his presentation.
Can you hear me?
Over to you, Dhiraj.
Can you hear me? Can you hear me? Hello?
Yes, this is audible.
Okay. Okay. Thank you, Devabrata. Thank you for the great introduction, and thanks for the invitation as well. I would like to share the screen. Just let me know if you are able to see my screen. Okay. Let me first. Can you see my screen? And is it full screen?
Yeah, this is perfect, Dhiraj.
Okay. Okay. Okay, thanks again. So as Devabrata mentioned, that I work on different aspects of cosmology, different direction, different subjects in cosmology I'm presently working on. Rather than going to individual topics, I would like to give you a crux of what I do in this lecture. So here today I'm going to cover the most interesting subject, that how do we observe the origin and the evolution of our universe. Okay, so to begin with, let me just ask a question that being a part of the universe, how is it possible to observe its evolution from the origin? So you know that we are in a vast universe. Probably the universe is 14 billion years old, and we are here on Earth only for a few million years. And if we try to capture the origin and evolution of the universe, it is indeed impossible with a video, with a telescope, with a video facility and things like that. So let's start with this concept that if we take a picture in staying in the Earth, what we observe in the picture, what we observe in still photo, captures a moment, right? So let's first see one simple picture: this spider building its web. Okay, let me just take a pointer from here. Okay,
Dhiraj, can you
uh,
be a little louder?
okay. I do not know why it is. Now is it fine, or is it still
It's a bit low.
okay? Let me
Okay, you
just
carry
try.
on.
Okay, no, let me just try. Just give me 10 seconds. I'll just try to see if there is some settings that I can. If there was something device, I made it 100%. So probably this is the loudest it can get.
Now this is fine, I think.
It's fine, right?
Okay.
Okay. Uh, okay. Now, as I was mentioning, that a spider is building its web. Now, what you see here, if you take a picture, just take one picture, you are seeing what is happening at that moment, at that second, when the picture was captured. Now, if you ask when the spider started building its picture, so the origin and evolution of the web, you will not be able to answer it because you need a video of that. Now it is definitely impossible to take a video of the universe for 14 billion years because those are past and you cannot take the video. Uh, so let's see how we can do that. So to go there, let's start with a length scale. So we define a length scale. For example, here is of the order of 1 centimeter, which is one fragment of this wave, spider wave. It's see that it is 1 centimeter. Okay, and from the light takes nearly insignificant time to come from here to here. Okay. Now, if you go to a larger distance, for example, I am here in Chennai and Devabhuta is situated at Kolkata, and the distance is 1,358 kilometers. And it is a picture or snapshot from the satellite, global satellite. And what you're seeing here is again another moment. The light takes really small amount of time to reach, go from Chennai and reach Kolkata, vice versa. If you go to larger distance, for example, India and US distance, it is 13,000 kilometers. And again, if a signal is emitted, it will be received in the USA in no time. You can because the speed of the light, as you know, is nearly 3 lakh kilometers, 300,000 kilometers per second. Okay, so whatever we see here is instant. Is we are seeing it as at an instant. So light takes really little amount of time to go from one place to another place. What happens if you look at our family, our solar system family? So here I have plotted different planets that are there in our solar system and also the sun. If you try to talk about the distances between the planets or the sun from any other planet, you will need many zeros in a kilometers. Okay, so kilometer is not a good unit to describe the distances here or farther. So we try to take a convenient unit and we call it astronomical unit. Okay, and this astronomical unit is one astronomical unit is defined as the distance between sun and earth, and from sun to earth light takes nearly 8 minute time to reach, and one astronomical unit in terms of our known unit kilometer is nearly 150 million kilometers. Okay, and if you see there are Jupiter, Saturn, and from sun the light takes even higher time to reach those because those are situated at larger distances. Pluto is here, for example, and if you see that from Pluto also it is at 39 or 40 astronomical unit from sun, from us as well. So if from Pluto it takes nearly 5 hours time to reach us. Now let's say Pluto is destroyed right now at this moment, we will get the news only after 5 hours because the news of the destruction that will be carried by the light is going to take some time. Okay. Let's take another view, another wider view, and we go on the neighborhood of the solar system. So the neighborhood of the solar system, as you can see now, we had 1 astronomical unit, then you have 10 astronomical unit, then you have hundreds, thousands, and 10,000 millions of astronomical unit. Then you reach Alpha Centauri, or the star, closest star, and then you see that zeros keeps on adding after in the astronomical unit. So we need another unit to describe the distances. So we go for light years. So it means that, so light year unit says that what the length that a light travels in 1 year. Okay, and from that also you can again define another unit which is extremely useful unit in the literature. Whenever you talk about cosmology, this unit is going to be your friend. And this unit is parsec. So 1 parsec is nearly 3 light years, and which corresponds to nearly 200,000 astronomical units. Okay. So when you try to take a picture of distant universe, you actually capture the time. While a still photo on Earth captures a moment, what is happening at that moment, but if you take a photo of objects that is staying far from us, you actually indeed capturing the time. So, and each point in the snapshot is going to capture a point in space and a time. This is true for all photos, as I have written as a disclaimer, but for small distances, time differences are negligible. So, in a single snapshot, we can expect to capture the evolution of the different parts of our universe. Also, let's talk about the Milky Way. This is the galaxy we are living in. Our star sun is one of the stars in this galaxy of the Milky Way. Here, the picture of the Milky Way is taken from Earth. And this is this European Southern Observatory's very large telescope, and the laser point is pointing towards the center of the Milky Way. If you go to the near to a galaxy, a very beautiful galaxy, we call it Andromeda Galaxy M31. To just give you an idea of the length scale associated to a galaxy, this is the radius of the Andromeda Galaxy. So light takes 100,000 light years, or 1 lakh light years, to come from the center to here. So if you are here and making an observation of the core of the galaxy, you will see the galaxy at 100,000 light years apart. So that means that whatever you are seeing now, the core of the galaxy, it is actually, you are seeing the galaxy, the core, when the core was 100,000 years older than today. Okay, so you are basically getting the information at different times when you are basically seeing at different parts of the universe. Here we are talking about the parts of the galaxy. We are soon going to see the whole universe that is visible to us. So this is going to be a notebook for the lecture, that whatever we learn, we will write it here. So what we learned, that each object in an image of our universe captures a time, and collectively they prove its evolution. Okay. Now we go to the full sky map. Full sky map means that you take the picture of the full sky. Here it is an observation of the 2 Mars extended sources, and extended sources means the sources that you can resolve with your telescope. And these are the distant part of our universe. And what you can see here is that these are the objects that corresponds to galaxy and other extended objects. The main point to take away from here is that wherever you see, if you take one large chunk of the sky, you will see that it is not different from any other chunk of the sky. So the observation that you can make here is that the universe, any part of the universe, in any direction that you can see, and you take the statistic, you count the number of extended sources, and you take any other angle and count the number of extended sources, you will find that these are very similar. If not same, they are very similar. Then you go to a different place, and here, let's say, you will see the same thing. So the statistics on the numbers that you are seeing at different parts of the universe and in different places in the universe are very similar. This is called homogeneity and isotropy. That our universe is same everywhere and is same in every direction. Okay. So this is a crucial assumption of cosmology that is supported by the observations, such as this observation. And another observation is done by this 2-degree freedom galaxy redshift survey, where you are just calculating the number of galaxies. Uh, Here, actually, I have plotted the number of galaxies. The 2-degree freedom observation has plotted nearly 250,000 galaxies in the universe, up to nearly 2 billion light years. 2 billion light years means 200 crores light years. Okay, so light takes 200 crores time to reach from here to here. So whatever point that you are seeing here is actually 200 crores years younger than what they are now. Here also you are seeing that the number of galaxies, you take any chunk here in any direction, you count the number of galaxies in this cone and in this cone. They will be same. If not same, they are very similar. Okay, so the statistics will be very similar. So again, this is supporting the homogeneity and isotropy of the universe. You can make another observation. So by measuring the temperature of the universe at different directions. Okay, what you do is that you send a satellite to space and you put it. Okay, sorry, there was speech that came in. Sorry, Devabrata, I think there is some annotation is going on, and some line has been drawn in this slide. Is it possible to remove that?
Or you just stop.
Hello, can you hear
Yes,
me?
you just stop share and share it again.
Okay. Okay.
Yeah.
Thanks. Okay. Uh, so what you do is that you take thermometer and basically measure the temperature of the universe at different direction. Here also remarkably you will find the same temperature at different direction, which is 2.7 to 55 Kelvin. This is precisely measured by telescope called COBE, Cosmic Background Explorer. What it measures is that the cosmic microwave background radiation. And this radiation is basically representing the photons that are streaming to us from the time it has last interacted with matter. I'm going to discuss next in detail what are the cosmic microwave background radiation. And so, in different directions, what you see is the same temperature. There are fluctuations. The fluctuations are 1 part in a million. So we can also calculate the fluctuations as I'm going to discuss. So what homogeneous and isotropic universe says is that the properties of the universe, such as temperature, number counts, are similar in every direction and in every place. But it is not true at small scales. For example, you can ask me that I'm looking at one direction, I'm seeing sun, and looking at the another direction, I'm not seeing anything. It is an empty space. So it is not homogeneous and isotropic at different direction. I'm seeing sun, which is a large mass, and in another direction there is no mass. It's the empty space. But this statistic, the homogeneity and isotropy, the statistics that support the homogeneity and isotropy comes at a large scale. So we talk about 100 megaparsec. So 100 times 10 power 6 parsecs. If you go to that scales and you compare the statistics, they will be similar. Okay. So what it says that since it is homogeneous and isotropic, it says that there is no center of the universe. Where we are, there is nothing special about it. It is not that we are the center of the universe. You can stay there, stay here, stay in some other part of the universe. If there is some other planet where there is some other observer, if they want to make some observation, they are going to see the same thing around them. Okay, so this is a crucial thing about the universe, and which makes our life a lot easier when we try to explain the universe, how it evolved from its beginning. So what do we do in practice is we use the Einstein's gravitational theory. Okay, so Einstein's gravitational theory relates the geometry of space-time to the energy momentum state present at that is the energy momentum of the object or energy momentum of the component that is staying at that place in the space-time. Okay, now this equivalently says the geometry of this universe depends on the dominant component present in the universe at any time. and the homogeneity and isotropy dictates the form of the metric. Metric means that, for example, if you want to calculate the distance between 2 points, it is x squared plus y squared plus z squared. Right now, if you go to special zero relativity, there will be 3 plus 1 coordinate, the another coordinate is going to be the time, and you can define the metric. Metric means that this is the scale with which you can measure the distances. Okay. Now, from the scale, you can get the geometry of the space-time, and you can equate with the energy momentum tensor of that is there, given the component of the universe which is dominant at that point and at that phase. Now, let me just give you another a number which I am not going to prove right now, but you just have to take it for granted that early observations suggested that the universe is expanding. Around 1920 to 1930s, Edwin Hubble did a measurement and showed that the galaxies are actually going far. Two galaxies that are distant, located from here, are going far from each other in different times. Okay? So if there are two galaxies, every galaxy actually are going far from each other, and the speed is actually, this is the current speed. What he has had calculated is a different speed, but the speed is actually 70 kilometers per second per megaparsec, which says that if two galaxies are 1 megaparsec distance from each other, then they are going to be going away from each other at a speed of 70 kilometers per second. Okay, so the universe is expanding. So if the universe is expanding, what is happening is that the universe was small at some point of time. Okay, so it has been expanding from a small volume. Now it has gained this volume that is today. So you can say that the universe was small at that some point of time. Now you can solve these equations, and you can find these relations that the matter density, if you have a matter in some space and you enlarge the space, if they expand the space, the density of the matter is going to reduce by a factor of 1 by r cube. So it will reduce as a proportional to 1 over r cube. The radiation density, the photons, they reduce by 1 over r to the 4, even faster. However, the dark energy density remains constant. Okay, which says that the universe, when it was very small, was dominated by radiations or photons. At some point of time, photons got diluted and it stopped interacting with matter because the number of photons decreased per unit area or per unit volume. Then it stopped interacting with matter, and then matter-dominated universe started after that. And after some point of time, matter also got diluted. What remained is the dark energy density, which was constant. There. All the radiation and matter fell apart, and there was the dark energy density. And this is the situation right now. So today's universe is. And when I said that the photon last interacted with matter, I was referring to this point in time where the radiation last interacted with matter. Okay. Now, let's take a note in our notebook that we live in a homogeneous and isotropic universe, and our position is not special. And the universe is expanding. The expansion has been driven by radiation, and then matter, and then dark, in that order. Okay. Now, let me introduce a concept of horizon. Okay. If I just plot whatever I have just said, is that there was some point of time when the universe was small. Let's say the observable universe was 0, the size of the observable universe was 0, and this point we call Big Bang. And from the Big Bang, the universe has started expanding, and we had this radiation-dominated era for nearly 400,000 years, and then there was matter-dominated era and cosmological or dark energy-dominated era, which stayed for 14 billion years. Okay, and what you can see here, what I have plotted here is the cosmic microwave background surface. Don't see at this yellow and green marks. I'm going to describe them in future slides. But what you're seeing here is the light cone. Light cone means that it is encapsulating the space which are causally connected. That means that light can travel in those distances. in that point of time. Okay, so this is the light cone from here to the surface of the last scattering when the radiation stopped interacting with matter. When this cosmic microwave background shows 2.755 Kelvin, the temperature and these two ends are same. Okay, so from these two ends, you know that the light is reaching to you, and they are showing 2.725 Kelvin temperature. Now you draw a backward light cone from here to the Big Bang surface. It says that these are the areas which were causally connected. Okay. Now this causal connection means that whatever happened there where can be. Let me go to. Sorry. Let me just stop screen share and start again. Okay. Let me ask, Devabrata, can you hear me properly now, or is there any disruption of the signal? Hello, Devabrata?
Yes,
Hello?
yes,
Okay, you can hear me, right?
yeah,
Okay,
yeah.
sorry. Okay, now let me get that pointer again. Now, the causal connection that I was talking about, it says that this part of the universe were in causal connected. So, but this point and this point were not in causal connection, which means that here 2.7255 Kelvin and here 2.755 Kelvin doesn't make any sense, because if some surface is in equal temperature, that means that there has been interactions. So light from one part has interacted with the light from another, interacted with the object and the object from another part, and everything was in thermal equilibrium. So the thermal equilibrium cannot happen with a faster than the speed of light, right? So causality has to be there. So these 2 points doesn't seem to be causally connected, but still they show the same temperature. So which is called horizon problem. The cones do not match. Light cones do not match. So to this is a communication problem, and just to describe to you this particular communication problem, I am giving you an example that you can think of a room with some high temperature in summer. Let's say the room has a temperature of 35 degrees Celsius. You haven't seen the room, but you know that the temperature is 35 degrees Celsius, and someone has turned on the air condition, and it takes nearly 30 minutes time to bring down the temperature of the room from 35 to 22 degrees Celsius. Okay. Uh, Here it takes 30 minutes of time. Now what you do is that now you enter the room. You enter the room in 5 minutes. You don't wait for 30 minutes. And you know that it hasn't got to 22 degrees Celsius. It takes 30 minutes, right? It takes the interaction, all the air conditioning to work, interaction in all corners of the room. So it should not have reached 22 degrees Celsius. But you enter the room, but notice that the whole room has a uniform temperature of 22 degrees Celsius. So this is the problem, that it is not physically possible if the interactions happen at a fixed pace or at a pace which cannot be exceeded. Okay, the signal cannot propagate faster than the speed of light. So one solution that we can find for this problem is that the room was 35 degrees Celsius. Then within the 5 minutes time, the room became 22 degrees Celsius, but the room was actually small at that point of time. So it was not that big. When you entered, the room became big. Okay, so this is the concept of inflation. It says that the universe from the Big Bang, right after the Big Bang, it had a tremendous acceleration. It had something like exponential acceleration that stretched all the parts apart. So let's say we have a small universe which was thermal equilibrium, but then you stretch it in all directions. It became big. And when it became big, you are seeing that all parts were in thermal equilibrium, although they are not in causal contact. They were in causal contact before, but you stretch them. Now they are not in causal contact, but they retain the information that were there before the inflation happened. Okay, so that is the problem. Again, going back to the same thing, this is the problem and this is the solution. It says that there was an inflation which actually made the light cones to overlap. So the overlap was possible by this inflation. It just inflated the universe from a very small, from a tiny amount to a very large amount. So what are the mechanism of inflation? So inflation gives a nearly exponential expansion of the universe, and it is driven by a scalar field. And it also seeded the formation of structure, the galaxies and everything that we are seeing today that are actually seeded by the quantum fluctuation that were initiated by the inflation. And it predicts the power spectrum. If you have the fluctuations or the quantum fluctuation, you can calculate the power spectrum of the quantum fluctuation. And if you plot the power spectrum, you will find the inflation predicts the power spectrum at a tilt, and also it generates primordial gravitational waves. This part we haven't yet noticed. This part we haven't yet detected, but we are thinking that we will be able to detect in future. And this inflation theory was introduced by Starobinsky, Booth, and Linde. So it was initially postulated pioneered by Alexis Starobinsky, and then after that, independently, Alan Booth and Andre Linde came up with the idea. Now, let's put it down in the again that before radiation domination, inflation broke the near exponential expansion of the universe. So there was scalar field dominated, there was radiation, then there was matter. Now it's dark energy. Right? Again, let's go back to the cosmic microwave background. 2.75 okay. Now, if you take out this mean temperature, as I said that this is 2.75 Kelvin, but there are tiny fluctuations, 1 part in a million. Now, from the map that you generate on the satellite, you just subtract the 2.75 Kelvin. There will be a CMB dipole. I'm not talking about that. Subtract that as well. What you will see then is this universe. These are the fluctuations with respect to the mean temperature. So temperature higher than that temperature, 75 Kelvin, are given in higher temperature colors like yellow, and that are lower are given in the lower temperature. Okay, so this was detected by the satellite probe, Cosmic Background Explorer, and George Smoot and John Mather got the Nobel Prize in 2006 for the getting the black body spectrum and getting the anisotropic spectrum. Let's talk about we had seen this in 1990s. What we could do, we could do in this time, we could measurements much better. So what was like standard definition, high definition. So there was standard definition TV, then there was high definition. We have ultra definition. So then there was this another attempt by NASA after Kobe was the Dickinson microwave probe. What it did, sorry, sure, here, you get very high resolution with very and high precision with much telescopes, okay, much detectors. So again, I show you. So whatever you are seeing, they were there, but now you can resolve each point in space. Okay.
Google
then there was Planck by European Space Agency.
Google Flight.
So what Planck does is this Planck satellite, as the typical cartoon of the satellite, the mirror, which receives the signal, and we send it to the Lagrange point, L2, which is 1.5 kilometers in the Earth-Sun system, Earth-Sun orbit, where the gravitational forces cancel, and it can stay there and map the universe. Okay, map the universe. So this is what it detects in the microwave frequency. The central red part is our galaxy. So during the analysis, we basically cut down that part. So these are the fluctuations with respect to the uniform temperature of 2.725 Kelvin of the cosmic microwave background. So you get the full sky scan by going to space, and then you project it here, and it looks like this.
Hmm?
These are the cosmic microwave background fluctuations as seen by Planck satellite, and this is the uh, position of our galaxy. Okay, you can correlate these signals. You can look at the sky and see that this is my delta T with respect to the uniform temperature. In the sky, you say this is delta T1 and this is delta T2, and the angle between them is theta. And you average it all over the sky. You take different thetas. This is the angular scale, this is the theta that I was talking about. And you can calculate the power spectrum. After recognition, you can calculate the power spectrum here. And the power spectrum looks like this. This has this type of features. Okay. Now you have your theory that you have your theory of radiation, inflation driven universe, then radiation driven universe. You get your theory and predict the curve and you fit to the data. That's how you get the cosmological, estimate cosmological parameters. So I'm not going into the detail of that, and also I'm slide. But let's just say one thing, that if you do this parameter estimation, you find the tilt that has been predicted by inflation. So I said that one crucial prediction of inflation is that it predicts the tilt of the primordial quantum fluctuations. Cosmic microwave background observation detects that tilt with a very high confidence. We have not detected the gravitational waves, primordial gravitational waves yet, but we are hoping to, as I said. Now, I made one more remark saying that the structures that we see today are actually originated from the initial quantum fluctuations. So there was initial quantum fluctuations, and then they got evolved. And you see the large-scale structure that you are seeing today, the galaxies and stars and all the network that you are seeing in the sky are all coming from that.
Parkinson disease
You can see here that they match beautifully. So this is the Planck's observation. You put it there, and these are the galaxy observation, the purple dots. The red dots. They actually fall on top of each other. Okay, so the large-scale structure observation also support that. What I'm doing here is actually you count the galaxies. Okay, you count the galaxies at different parts. There you are counting you are computing the delta T, the difference in the temperature. Here you are basically counting the galaxies and then correlating over the sky. Okay, then you are plotting the power spectrum here. So what you find is that they actually match. But again, let's note down this fact that the initial fluctuations actually seeded the formation of the large scale structure. Okay. Now, let's talk about another observation that was also very important in the last 2 decades. Is the observation of the supernova. So if a star dies in an explosion in the two-star binary system, we call it a type 1A supernova, which has a similar absolute brightness. So all the supernovas that actually explode like in this system have similar peak brightness. So you can understand them as standard candles. Okay, it's like a 100-watt bulb that is there in different parts of the universe. Let's say now from the bulb that is farther from that is situated farther from us, we are going to see their brightness reduced compared to a bulb which is closer. So we can use them as standard candles, and you can understand what is the distance of that supernova from us. So we can also understand what is the cosmology that we are living in. What is how the universe is expanding. And the cosmology, how you can constrain your cosmology is that you observe the brightness of the supernova, and you observe a lot of them at different distances, which also correspond to different times. Get the matter and dark energy densities, and find the expansion rate of the universe, and find the acceleration of the universe at the same time. Okay, so let's plot them. So these are nearly 580 supernova from Union 2.1 supernova samples, and these are I have plotted the distant modulus. You can see them as the brightness. Okay, so and if you plot this with respect to age, for example, you have to be careful. I have plotted them as a function of age, but this changes with parameters. So the best thing is to plot them with redshift, but I have not introduced the concept of redshift. So Let's put that as a function of age. So today is 14 gigayears. So if we go back in time when the universe was 4 gigayears older, you get the information about the supernova, you plot them. And if you say that what is the cosmology, what is the prediction of the cosmology if there no matter is there? Okay, so I said that the universe is dominated at different times by matter, dark energy, and radiation, like that. So if we assume that there was no matter, the universe was dominated by dark energy, then the curve that you get, the theoretical curve that you get is like this. As you can see that it doesn't fit the curve well. I'm not giving a statistics, just giving a visual interpretation of this thing, how the parameter estimation is done. So this is not a good fit to the data. Okay, most of the data are lower than this. If you have zero dark energy, if you don't assume any dark energy, say that the universe is dominated by matter only, then you see that it is not fitting well the data, right? Now I put 30% of matter and 70% of dark energy. You see that it goes nearly through all the points and they are within the error bus. Okay, so that gives you the idea that we are in a universe where the 70% of the energy budget is given to the dark energy and 30% is given to the matter. And given the dark energy, the universe accelerates. Given the 70% of the dark energy, you can calculate the acceleration parameter of the universe. You can say that the universe is accelerating at the moment. And for this discovery, Rees, Perlmutter, and Smith got the Nobel Prize in 2011. So let's write down the final part that we had learned, that the universe is presently in a state of accelerated expansion that's driven by dark energy, which occupies 70% of the energy budget of the universe. If you plot the whole notebook in a single picture, this will look like this. The universe started with a point and it inflated. There was cosmic inflation. Then there was the radiation dominated era, this yellow part. Then there was this cosmic microwave background. Then there was this matter dominated era. And the structure started to form, the galaxies formed and all that. And now we are in a cosmological constant or dark energy dominated era, say generally. Okay, in one of the dots, you can find cluster of galaxies. Within the cluster of galaxies, you can find one galaxy, and in one galaxy, you can find the solar system, from where we actually began this lecture. Okay, now let me talk about two efforts where I am a part. So one effort is called CMB Bharat. As I said, the Planck was the with Planck, we got ultra high definition image of the universe. What's next is the CMB Bharat that we proposed to ISRO as a joint ISRO and ESA European Space Agency mission. We are planning to detect the primordial gravitational waves with very high number of detectors and with very high sensitivity. So this is the diagram of the telescope that we are planning, and it can be launched through this GSLV Mark III in the same place, Sun orbit. And these are the specifications. It will be 2 tons. It has a diameter of 4.4 meter and all that, and it will have 2,400 detectors. It is one of the design. Okay, we can also constrain neutrino mass to an unprecedented accuracy, and understand the DNS, and I haven't talked about that. You can also understand the small scale physics. You can understand the galactic physics and primordial magnetic fields and many other things. We call the satellite the project ECHO, exploring cosmic history and origin, and it is a near ultimate CMB polarization survey. And this is the working group. We have different working groups, and I've taken it from the Dhiraj, Tarun Sarodip's site. Tarun Sarodip is at ICE Pune. And we analyzed what could happen with the CMB Bharat, with the ECHO. We took the sensitivities, projected sensitivities, and we tried to find how better we can constrain our physics. And we proposed this to ISRO in April 16, 2018. It is now under review. There is another thing is that another survey is called Euclid. It is an European Space Agency mission. I am also a member of the survey. It is going to measure, it is going to launch in 2022 or 23. The latest news was 2022. And it's going to measure the shape of billions of galaxies and observe spectra of millions of galaxies and clusters within the last 10 billion years. So it is going to be a massive survey. So using that, you can do lots of statistics, and you can understand the geometry of the universe, nature of dark matter, dark energy, etc. You can also test the modification to Einstein's theory of gravitation, also consider primordial physics. Specifically, what I do is I work on these areas. Already, Debabrata mentioned these areas, but let me just give you one-page summary of this. So you had inflation, as I mentioned. I haven't described the reionization, but I also work on this. I try to constrain the theory of inflation and theory of reionization by using CMB and large-scale structure data. Large-scale structure data is the data of the galaxies that are far away from each other, get the large-scale information, and constrain these things. These are the few publications that I just want to share in this slide. So these are on inflation. With inflation, we came up with inflation in this collaboration, and this is one model of inflation. I wrote a code called Bingo, which was the first public code to calculate the primordial Gauss spectrum and primordial bispectrum as well, the three-point position function. Also, the modified Richardson-Lucy algorithm was there, so which is a pure data analysis from CMB, just trying to understand how the theory looks like if the data is given. On large-scale structure data, I worked on this Euclid forecast, independently from the Euclid collaboration, and also I'm presently working on the primordial black hole and stochastic background wave production from different mechanism of inflation. So with that overview, I would like to stop here. Thank you. So if you have any question, you can. Should I stop the screen share?
Thank you, Dhiraj, for your very lucid and illuminating lecture. And your slides are perfectly arranged for the student as well as the academic communities, I think. I just forgot to mention Dhiraj has just published a PRL a month ago, as far as I remember, Dhiraj. And about his research profile, he's a very bright career in research, about 19 or 20 age index. I just forgot to mention during his introduction. He has also published very high impact journals in well reviewed publications. So with this, I would like to thank Dhiraj for his nice presentation. Now the session is open for questions, and before that I would like to introduce our convener, Dr. Shishendu Sarkar. And Shishendu, are you there?
Yes, am I audible?
Yeah. Just go on with the questions and answer session.
Okay. Let me introduce myself first. I am Shishendu Sarkar, convener of this webinar. So I was little late to join here. So this is the time for question answer session. So I have a small question before going to ask, take any other question. That what is the source of energy that is accelerating space?
So we call it a dark energy. The thing is that we do not know the exact nature of the dark energy. We actually explain it with its equation of state. So the equation of state, we think that it has a negative pressure. So P is proportional to minus of rho. Okay, rho is the energy density. So that's why it is actually ripping the space apart. So it is there since the beginning. So since, as I said, it is a cosmological constant, it is there since the beginning. There is a possibility that it is a cosmological constant. Now, Einstein's theory says that the geometry you can equate it to the matter, right? So there is this covariant derivatives, and you can basically integrate them to get that equation. In the integration, you find that integration constant, which is the cosmological constant. That you can equate it as a source of energy. So we are still not sure that it is the cosmological constant that is driving the universe now, but at least all the observations that we have till now supports that it is a cosmological constant. Where your P is actually not just proportional to rho, P is actually minus rho. So the W, so if you write P as minus, P is equal to W of rho, W is equal to minus 1. So you have a equation of state, which is -1.
Okay, thank you. So I'm taking another question from Indranath Bhattacharjee. Tell something about phantom dark energy in perspective of increasing density. Which kind of energy condition is valid in phantom era?
Okay, so see, from the observations, you can only constrain the W of Z, right? Okay, let's not talk about the W of Z. Let's say W of time. W is a function of time. When I say W equal to -1, we are assuming that it is constant, and it is constant with a value of -1. But W can be a function of time as well. So when W goes less than 1, that we call a phantom dark energy. Okay. So there are different theories that can give phantom dark energy. You cannot get it from the normal gravity. You need modified gravity. Okay, so these are a bit different or difficult topics. So from the modified, so if you write a Lagrangian, your term in the Lagrangian in Einstein gravity is going to be R, the Ricci scalar, if you know what I'm talking about. But if it is not the Einstein gravity, if you try to make it modified, make a modified version of it, you write it as a f of r, function of r. Okay. In some function, you can find it as a where the you can find the dark energy where the equation of state can go below 1, and those parts we call it as a phantom dark energy. Okay.
Okay.
And dark energy, in some sense, is also compatible with the data. It is not ruled out by the data. It is there, supported.
Okay, another three questions from Vikramjit Chandra. So first one is, what is favorite model of inflation is?
Okay, so let me go through one by one. So what is the favorite model of inflation? Okay, so inflation gives you gives different. Okay, so this is something that I should share a slide because I have a slide for this one. Let me just share my screen again. So this is a very interesting question, and it just that it loads. Okay, I think can you see the slide? Can you see the picture in the slide? Can anyone please unmute and say that they're seeing the slide?
Yes,
Okay,
you may
it's
proceed.
visible, sir. Okay, great. So this is something that is a bit involved, so I skipped this thing. But since you have asked, it is better that I explain this thing. So as I said, that inflation predicts something. It predicts the tilt of the power spectrum, and it also predicts primordial gravitational waves. Okay, the primordial gravitational waves can be given with a tensor to scalar ratio of r. Okay, I'm not going to the detail. So, for example, different values in the y-axis gives you the values of the magnitude of the primordial gravitational waves, and this one, the x-axis, is the tilt of the primordial scalar perturbation. Okay, so this is ns. We call it ns. So when you ask me that what is the best model for inflation, it always changed. So this is the recent story. So earlier the curve was like this. This is the constraint on the models. Okay, the models, for example, are given in this blobs, in this circles, and the constraint is given by these ellipses. Okay, that means that if something is outside this ellipse, it is ruled out. It is not there in the literature, so that it is not there in the observation. So observation said that this model is not favored, so it is rejected. So since the beginning of inflation, many models has been rejected just because we got to know about our cosmic microwave background much better. So you know about you send the satellite, you improve the satellite, and send another satellite with much improved machineries, and then you can get these lines. You compare your theory with the data, and these are the constraints. Now you can see that some models, for example, are staying at the center. Okay, So there is a Starobinsky model of inflation, R square inflation, that stays in the center. So probably people are thinking that this is the sweet spot where the best model of inflation is staying at. So we haven't detected the dark energy. Sorry, we haven't detected. I'm sorry, detected the primordial gravitational wave. So R is equal to 0 is still compatible with the data. If we detect it, then there will be a circle like this. So it is bounded in the NS direction. As you can see that we have rejected this model of inflation. We have also rejected this yellow model of inflation. But this model of inflation stays in the sweet spot, okay, which has very little primordial, which gives very little primordial gravitational waves, and it actually gives a spectral tilt, which is very close to 0.96, which is at the center of the contours, which is the center of the constraint given by the data. Okay, so if you have any further question on the data constraint, please ask me. I can explain in more detail. But if you have understood, then it's fine. Okay, then
So we can take another question.
sure.
Okay. The same person asking that a brief comment on his opinion on the current crisis in cosmology, the disagreement on the estimation of the Hubble parameter.
Oh, okay. So we know a lot the current topics. Okay, good. So as I said, the H naught, as I have given an idea about the H naught. H naught is basically your expansion rate. Okay, the Hubble constant we say. So the expansion rate today. So we measure it to be nearly 70. Okay, 70 plus minus something. So it means that two galaxies that are 1 megaparsec apart from each other are receding from each other with a speed of 70 kilometer per second. Okay. Now, if two galaxies are 100 megaparsec apart from each other, they will be receding from each other by 7,000 kilometers per second. Okay. So the crisis in cosmology means that you make one observation and you make another observation which constrains this parameter, this Hubble parameter, and then they don't match. What happens is that I gave you two examples. One example is the supernova. Not exactly this supernova. You can also get the supernova which are staying very near to us. Okay, you take those supernova and you calculate what is the Hubble constant. So the person who got the Nobel Prize, Adam Rees, he finds with his observation, it is 74 plus something like there is a 1.4% inaccuracy. So the 74 plus minus. While this Planck constraint is 67 plus minus 0.4 or something like that. So you see that even, so there are error bars, but even in that case, there is a difference of 67 and 74. And these two observations are extremely precise. Extremely precise. These are so precise that they are saying that there is a huge discrepancy between these two numbers. Okay, so now you ask me what is my opinion. So they are okay. My opinion is that I can give you information. So there are lots of works that are going on. One part, which is one person, who is in the Perlmutter's group, the another Nobel laureates group, he is saying that it is our systematics. We are not taking the data or analyzing the data properly in the supernova. So that is the thing. So the host galaxies, there are old galaxies and new galaxies. We are basically not calibrating them properly. There are other people, for example, Rees, who got the Nobel Prize. He is saying that no, there is some new physics in it. Maybe this is a phantom dark energy, or maybe this is something else, some early dark energy model and things like that. Yes, so this is an open question in cosmology right now, which is there for the first data release of Planck. So when you saw the Planck data in the screen, which basically they broadcasted saying that H naught was 67. We thought, oh my God, what happened? H naught was 67. It doesn't match with that. So over time, the crisis again became even worse. So both part has made their newer predictions, newer constraints to be more precise. So the crisis is now even worse. So it is an open question. Okay. And the thoughts on the slow roll inflation as a whole after the release of the Planck data. Yes, slow roll inflation, with particular slow roll inflations are actually there in the are supported. So slow roll inflation. So inflation has to happen with the slow roll. So if a scalar field rolls slowly down to the bottom of the potential, that have the that gives the inflation, that gives the exponential expansion of the universe. So yes, Planck actually predicts, or Planck actually supports slow roll inflation very strongly. Okay. Any other questions?
Uh, Someone Partho Sarkar asking that can we measure the nature of dry energy by the help of machine learning? Sorry, dark energy by the help of machine learning.
No. Okay. So the thing is that you have data and you have theory, and machine learning is just a tool that you say that you have different predictions from the theory. Now you just do not vary the parameters. You just see that what is the pattern. Machine learning tries to understand the pattern, and from that it tries to give you a picture of the universe. To understand or to measure the nature of the dark energy, you need observations. You need hardware. You need things to go to space, or you need telescopes to be built in the on the Earth and make precise measurements. Okay.
Dr. Kuntal Sinha asking that is there any limit up to which the space can expand?
Okay, so the thing is that, as I said, two galaxies, one per megaparsec apart from each other, are expanding with a speed of 70 kilometer per second. Okay, so if the galaxies are much larger away from each other, for example, they are 14 gigaparsec away from each other, which is the horizon today, then they are actually going away from each other with a 14. What is the megaparsec? Okay, so it will be 14 times. 1000, so 40,000 times 70, so that will be the speed, so with which they are receding apart from each other. So really fast, so there is no limit. It depends on what the dark energy, the nature of the dark energy, the equation of state of the dark energy.
Subayu Bose asking that is it possible by any means that because of the expansion of the universe, even the dark energy gets separated out and something else dominates?
Dark energy gets separated out. We know that dark energy is actually a constant. We know, or at least it is very close to a constant. So actually, what happens is that if okay, so this is how the theory and observation of the discoveries happen. You have a theory. Before the dark energy and dark matter, nothing was there. Okay, you know that there was this radiation because we have seen photon. We have okay, so we know that there is radiation because of our daily experience. We haven't seen photon, but we know that photons exist because of our experiments, and we also in daily life we know the photons because we light a bulb, it affects the place. So that is radiation. There is matter, so whatever we are surrounded by is matter. So then we didn't need any other things to explain. What we did is that we had this theory and then we compared with the data. As I said, what happened is that we could not fit the data with zero dark energy. That's when we said that we need something that says that we need something that rips the space apart. So that is expanding the universe. So that says that we need the dark energy. So we put the dark energy. Also, dark matter was put in a different perspective. So this is the theory of the universe right now. As of now, we do not need any other thing. So we do not have any evidence or any signal or any clue from the data that says that we need any other things other than the compared to the dark energy. If there is any other form of any other component that is so if the dark energy is not constant, it is smaller than that. Let's say it has a smaller expansion rate compared to the smaller decay rate compared to the radiation and matter. If there is some other things, let's say, in that case, maybe at some point of time that is going to take over, which has even smaller decay rate, but we haven't found that. We haven't, sorry, we do not have any clue, so we don't need that, so we don't put it in our theory. Okay. Please, another question is that how does gravity affect time? Right. So how does gravity affect time? So that can be done from the simple, okay, not simple, but general theory of relativity, right? So if you have a mass at any place, for example, sun, it is bending the space time. Okay, so that's how the gravity affects time. So it is bending the space time around you, and the gravity. Okay, so and then the perception of time and all the other things changes. So you can just see in a textbook on the general theory. And, okay, any other
So,
question?
other question from Bapan Goala, that can we use dark energy as a regular source of energy in future?
Okay, it's not okay. So it is an energy that is there in our universe. So it is not a regular in terms that yes. So at some point of time when the universe will expand, so 30% of matter is also going to decay. So decay means that it is going to be matter will be there, but it will be diluted if the space expands. So 30% will go to nearly 0.1% or even below that. So at some point of time, it will be completely covered by dark energy. If dark energy has equation of state of -1, and there is no other component of the universe. So it will be there. So every part of the space is going to rip apart.
Okay, the last question from Rashmi Gupta, that can ordinary particles decay into dark matter?
Well, these are we don't know yet. So there are different things. There are different experiments going on Earth, and also people are thinking that whether dark matter decays into matter and things like that. So these are the things that we have not been able to tell because our observations are not precise or not that precise, or our experiments haven't gone to that small regime to answer that. So yes, I do not have any solid answer to that.
If anyone have question, please unmute yourself. Otherwise, we will conclude the session. So, if anyone, there is no one. Okay. Thank.
I'm sorry. May I ask just one question?
Okay. You can proceed.
By the way, Dr. Hazra, thank you so much for the talk. It was quite nice. So this actually goes back to the first question I'd asked earlier. I was the one who asked those three questions, including the Hubble parameter and things. I actually wanted to know what your favorite model of inflation is. Like that being.
Okay, so so you have seen the power spectrum. Okay, so we cannot take a peek. What I am doing is that even today, what I am trying to compare with the data. What today morning when I came, the result came in, and I'm still analyzing the data and getting comparing with the data. And working with a lot of inflation models. For example, the model that I gave with the people with Arman Shankapillu, George Smoot, and Alexis Starobinsky. So I have also discussed these names before in this lecture. So this is called drift inflation and weekly bit inflation. That actually what it does is that you get the fit to the data pretty well by the slow roll inflation. But we showed and that there can be certain changes in the potential of inflation, which has slow roll, but there are intermittent departures from the slow roll, and that gives you some signal that fits to the data well, data better than the standard model. So if you ask me my pick, I will say that okay, this week I like weekly with inflation or with inflation that I propose with my collaborators, but definitely we have not been able to. This gives you a huge improvement in fit to the planned data compared to the other models that are there in literature. But I cannot be prejudiced. Over time, I have been much less prejudiced about my model, and I'm trying to explore other models like two-field inflation models, which I'm presently working on with other people and trying to compare the data. So there are various models, and I'm trying to find the best ones. So as of now, weekly inflation is definitely one of the candidates, but there are others as well. So I cannot take a peek. I'm sorry about that. But,
Thank you so much, sir. I'll have a look at the video. Thank you.
sure.
Can you mention your name, please?
I'm sorry. My name is Bikramjit Chandra. I'm a faculty member from Solution College.
Okay, thank you. So, any other question from audience?
Hello, sir. I'm Shivayu Bose from Stellation College. I had the same question as I asked the last one. Like, is there something like we are near an object which has used gravitational force? A time dilation takes place. So, what if I'm staying on Earth and a person in space? Who will age faster, me or the person in space?
Sorry, I could not hear the last part of your question. The time dilation you're talking about. Time dilation happens in this in the special theory of relativity as well, right? So if a person is actually going from, okay, so these are like these paradoxes that you will learn in the literature. That you are asking that if some person takes a tour of the world of the universe and comes back, whose clock will be dilated, right? Whose age is not going to increase as fast as the other, right? Isn't the question?
Yes, sir.
Yeah. So
Yes, yes.
the person who is traveling is going to be that clock is going to be slower. So that person's age is not going to increase. Now there is a paradox that relativity says that with respect to that person, you are moving, right? But actually, it comes when you say that who is actually moving by saying that that person, let's say your friend, is at rest with you right now. Then it takes an acceleration and then gets the speed and then goes around the universe and comes back. So and also then decelerates. So and then stops. So this acceleration has the key. So when you go around the universe and come back, the person who is actually taking the acceleration and coming back, his or her clock is going to be back.
So just a simple more question, sir. You said that the person will be roaming here and there in the space will be, his time will be a little slower than mine. So in the film Interstellar, the person in the Miller's planet, he was still there in the planet, while the person just outside the planet, he aged faster. How come that's possible?
Sorry, tell me again. In the Interstellar, I forgot the Interstellar movie. Actually, there was this black hole in which there are lots of things. So sorry if I am not able to explain that correctly. But you are asking something, saying that there was one person in a planet. His age was not increasing, but in Earth it was increasing more because of the tidal. These are tidal forces, right? So that so you can find it in gravity textbooks, but actually I am not able to connect to the movie right now. So I had seen the movie, but I really didn't think afterwards that what has shown there, and so
Excuse me, sir.
sorry, I became
I have asked a question earlier. No, I have one more question. That is, during the inflation era, there was no dark energy. But in the model of inflation, can we get influenced or inspired by the model of inflation to apply in the dark energy? Because there is something similarities there. Because in the inflation there is a lambda, and also in the dark energy there is a constant density, kind of constant density. So is there any inspiration from the inflation model to apply to the dark energy?
exactly. Okay, this is a very nice question. Okay, so what inflation does is that it expands the universe nearly exponentially. So for that you need a particular type of potential, and it is scalar field. So that has to be much fast. So you must the scalar field must roll very slow. So that is the construct. Similarly, some other thing that is expanding the universe is called quintessence. Okay, that also you can describe by a scalar field. It doesn't give that much expansion, but it gives you the acceleration that you need. Okay, so that is also called quintessence thing, which has a W. W of t is greater than or equal to -1. Okay, so there also you can define a scalar field from the inspiration of inflation. You can also define it here. But again, we do not have any constraint as such on the model, any tight constraint, or we have not detected any quintessence model yet. So what happened during the inflation is that the scalar field came down and it decayed to particles. Okay, so that reheated the universe. So that did reheat the universe. So we got the particles from there. Okay, from using the particle production mechanism and all that. So that's where the inflation decays. Now there can be some other mechanism that some energy has stayed there as a constant, and radiation came in, radiation decayed, matter came in, matter decayed. Okay, they were there, but matter came in as a dominant component, matter decayed, and then finally that part of energy remained. But these are some things that are at a speculation level. Okay, something that we cannot just pin down as of now. So we really need much more data and much more models and things like that. So specifically, much more data compared to the models. So there we can only then we can try to answer this kind of questions. But this is a very interesting.
Yeah, thank you.
Okay, we have taken enough question in the question answer session. So we must conclude our session now. So thank you very much, Dr. Dhiraj Kumar Hazra, for delivering such type of presentation here. And I must say you are so much energetic person to answer such type of questions. So thanks once again, Dr. Dhiraj Kumar Hazra. And so for dear participants, we will send feedback form through mail and also certificates. And those who do not get certificate within 5 days, please feel free to mail us. Thank you very much.
Thank you, Dhiraj.
Thank you, Devduta. Bye.
Bye.
Thank you.
That's it.